Sublimation. So here we have an illustration of a block of ice. Here are little Mickey Mouse water molecules, and they're arranged in a crystalline structure, and all of them are vibrating. They have an average kinetic energy based on the temperature, but some have a higher and some have a lower. And so if you have some at the edge that happen to have a high kinetic energy, they may have enough kinetic energy to escape from this crystal lattice and go from a solid directly into a gas. That's called sublimation, going from a solid to a gas. There's no melting involved. So sublimation is a solid to a gas. The opposite is called deposition, going from a gas directly to a solid without passing through the liquid.
So is that why we see smoke coming out of an ice?
No, when you see what looks like smoke near an ice cube, that's actually the cold from the ice cube is sucking heat in from the air, cooling the air, and the moisture in the air is condensing into a liquid, and so you see the vapor like a fog. Yeah. So solids also have a vapor pressure because some of these water molecules will escape into the gas state. Do you think this is higher or lower than the vapor pressure for the liquid? Lower. It's much lower. Yeah.
But in what reason do we have that
Sublimation? It happens. It happens all the time. You have a freezer at home?
Yeah.
There is sublimation occurring in your freezer right now. So if you have an open container, sublimation will happen more because the water molecules that escape into the gas can then float away. And if it's in your freezer, they're going to float away till they run into something. That something is going to be cold and they're probably going to stick. And that's how you get frost on the inside of your freezer. Like, who put all this water, this ice on the side of the freezer, right? The modern refrigerators and freezers have an automatic defrost cycle that helps to get rid of that. But if you have ice cubes that have been left in your freezer for a really long time, they're going to be smaller than they originally were because some of it sublimes. You've heard of freezer burn, right? Your food gets kind of dried out. You find an old bag of tater tots, right, in the back of the freezer, and you open it up and you dump them on a pan to cook them, and it's like half full of ice crystals. Like, who the heck would put ice crystals in the bag of tater tots? Well, they weren't there originally. That was water that used to be inside the tater tots, but it's sublimed. It moved out of the tater tot into the gas state. It was in this sealed bag, so it couldn't go anywhere. And so it eventually just formed crystals of ice in the bag. If you use a deep freeze that's colder the temperature, the less sublimation. Or if you seal up your food so there's no airspace. So you wrap it very tightly in foil, or you use a food saver bag that sucks all the air out. That also reduces the sublimation because then there's nowhere for those more energetic molecules to go. This is a picture of dry ice, and here's that smoke we were talking about. It looks like there's smoke coming off of this, but that's actually more like a vapor trail. So there's moisture in the air around the dry ice, and as the dry ice is trying to, well, it actually doesn't melt, it just sublimes. It sucks energy in from the surrounding air, making it cold, and then we see the water that's in the air condense into a liquid that we can see. Dry ice is solid carbon dioxide. And the reason it's called dry ice is because carbon dioxide does not melt at atmospheric pressure. You cannot have liquid CO2 at atmospheric pressure. It's just not possible. So normal ice is wet ice, right? When ice melts, it gets things wet. Well, there are situations where you don't want that. Like if you're shipping pharmaceuticals or some other thing that needs to stay cold, you don't want your package leaking all over the place. The post office is going to be pretty upset about that. But you can use dry ice, and as it stops being solid, instead of melting, it sublimes into the gas state and just escapes into the air, and it's not harmful. So people are okay with that. Any questions? Fusion is another word for melting. Okay? So you take a block of ice and you heat it up, and it begins to melt, right? As you heat it up, the molecules, those are the words, the molecules vibrate faster, right? They have greater kinetic energy. At some point, at the melting point, the molecules have enough thermal energy to partially overcome the intermolecular forces that are holding them together as a solid. They're still connected to each other, but now they can slide past each other, and so they can become a liquid. So melting or fusing refers to the transition between a solid and a liquid. I remember that fusing is melting because I think about chocolate chips, and you put chocolate chips in a pan on the stove and you heat them, and what happens? They fuse together, right, into one big liquidy, chocolatey, yummy thing. So fusing is melting. So just like with boiling, what we see is you take a solid and you add heat to it, the temperature of it increases. When you get to the melting temperature, then the temperature does not increase until all of the molecules have made that transition from a solid to a liquid. If you're adding more and more heat, you're just like, I want this temperature to go up. It'll melt faster, but the temperature won't rise until all of it's melted and turned into a liquid. Then the temperature will go up. The opposite of melting is freezing, going from a liquid to a solid. And you do need to know these terms. They're not too hard, but they can be a little confusing on a test. So freezing is liquid to solid. Any questions? Of course, there's energy involved in melting and freezing, just like there was in vaporization and condensation. Melting is an endothermic process. We should be able to think that through. We've got an ice cube. If we want it to melt, are we going to put heat into it or take heat out of it? We put heat into it, right? Fast way to melt an ice cube, stick it in a pan and stick it on the oven, on the stove, right? Turn the burner on. Put heat into it, it'll melt. It's an endothermic process, energy goes in. So the amount of energy is called the heat of fusion. So delta H, FUS for fusion. And that's the heat needed to melt 1 mole of a solid at its melting temperature. So for water, this value is 6.02 kilojoules per mole. Freezing is exothermic. It's the opposite. If melting is endothermic, then freezing has to be exothermic. And the same amount of heat is released when something freezes. So we've been having trouble with our refrigerator lately, not freezing. What your freezer does, and the refrigerator, but we're talking about freezing here, is it is pumping heat out of the freezer box, right? We won't go into how it does that, but it's pulling heat out. And that causes your food or your ice to freeze, right? It's an exothermic process. You can make it happen by sucking the heat out of it. Stuff doesn't just freeze spontaneously at room temperature unless room temperature is below the freezing point. So I live in Reedley, and we are surrounded by fruit trees and vines. And in the winter, a freeze is a problem because the citrus can freeze. And if the oranges freeze, they're no good because freezing, the water expands, it breaks the cells, and the fruit turns to mush, right? And then everybody's in trouble. So what they do when a freeze is forecasted is they water the fields. They get a lot of water out there. You want some standing water. And then they also have these big wind turbines. It sounds like the whole city's going to take off in the middle of the night, all these things going on. And they blow the air around. What happens is the water on the ground, as it freezes, it releases energy. Because as it freezes, it's going to stay at 0 degrees Celsius or 32 degrees Fahrenheit until it's all frozen. And so as long as you still have some liquid water left to freeze, it's going to release energy and it will not let the air temperature near it go below 32 Fahrenheit. Well, to freeze an orange, you have to get down more like 26 for like 4 hours. And so even if the temperature gets down to 26 or 25, by flooding the fields and blowing the warm air around, they can keep the crop from freezing. So I think that's a cool application of thermodynamics in citrus farming. Any questions? So heats of fusion are generally much less than heats of vaporization in magnitude. And that's because you only have to partially overcome the intermolecular forces. You don't have to completely break away. So if we compare, here we have heat of vaporization in the pink and heat of fusion in the blue. So to melt the water is just above 5 here, it's 6 kilojoules per mole. To boil water, it's over 40 kilojoules per mole. It's a huge difference. Because in order to go from the liquid to the solid, you have to break all of the intermolecular forces. In a liquid, you're breaking some to move away, but then you're forming others, and so you're just sliding around, and it's easier. The magnitude of the heat of fusion is going to depend on the strength of the intermolecular forces. If we look here, we've got water, rubbing alcohol, acetone, and diethyl ether. The heat of fusion is going to be stronger in general for substances that have stronger intermolecular forces. You see here that diethyl ether is even higher than water, and yet its heat of vaporization is less. So there are some trends, but they're not really very strong. Okay, so this is another section. I'll start.